Welcome to Thermodynamics Screencast number 2 for Chem 1B at Shasta College. Let's start by looking at something we saw in Chem 1A, which is the first law of thermodynamics, which states that in any process, the total energy of the system and its surroundings is constant. So this is also known as the law of conservation of energy. And when we have a system doing whatever it does, so maybe we have some substances reacting in a beaker or a flask, that system, when it does whatever it does, may produce some energy in the form of heat. It may take in some energy in the form of heat. It might do some work. It might have some work done on it. But the net amount of energy that goes into the system or out of the system is going to go to the surroundings or be taken from the surroundings. And if we look at the relationship, the change in energy of a system, it has to do with how much heat goes in or out of the system, how much work is done on or by the system, and the total amount of energy is going to be the same regardless. So some energy may go out of the system into the surroundings or out of the surroundings into the system, but no energy is lost in the process. Now we're going to focus a little more on the ramifications of the second law of thermodynamics, which one way of stating it is in any spontaneous process, the total entropy of a system and its surroundings always increases. So this is often stated as the entropy or disorder of the universe always goes up, and we will look at this via one way to define entropy, sort of on a macroscopic scale. The change of entropy is the amount of heat that goes into or out of the system divided by the temperature, and the temperature, of course, has to be in Kelvin. So let's say we have a system and we are tracking its entropy change and its enthalpy change. Now that's what we've done so far. We've looked at the entropy and enthalpy change of the system together with the temperature. That gives us the Gibbs free energy change of the system, and that tells us whether a process is spontaneous or not. But we have to remember that when the system does whatever it does, there's also going to be an entropy change of the surroundings. And we'll look at a specific example of that in just a bit. But here's the statement of the second law of thermodynamics, or at least one way of stating it. The total entropy change is equal to the entropy change of the system plus the entropy change of the surroundings, and that total is always positive throughout the universe. And for a spontaneous process, the delta S system plus delta S surroundings will be positive. So if we have a system where the delta S isn't positive, it could still happen if the delta S of the surroundings is big enough. And this is one way of stating the second law of thermodynamics. So here's a specific example. We're going to look at a system where delta H is actually a negative number. In other words, the process we're looking at is an exothermic reaction. So if that's the case, the system gives off heat, and the heat flows into the surroundings. And if the system gives off a certain amount of heat, then the surroundings take in that amount of heat. So delta H system we could represent by Q for the heat flowing in this case, out of the system. Let's say it's 2,000 joules flows out of the system. Well, that means 2,000 joules is absorbed by the surroundings. And so the delta H of the surroundings is the opposite in sign but same magnitude as delta H of the system. So we can say delta H surroundings is equal to negative delta H system. And now, since the delta S of the surroundings is Q over T for the surroundings, that's one way of defining entropy. One way of defining entropy, yes. Then Q is delta H of surroundings for the surroundings, and it's equal to negative delta H of the system. So the delta S of the surroundings turns out to be equal to negative delta H of the system, and that's divided by T. So delta S total is delta S system plus delta S surroundings, and we just figured out what delta S surroundings is in terms of delta H of the system. So let's plug that in. Delta S total is delta S system plus negative delta H system over T. And in general, for a spontaneous process, delta S total equals delta S system plus delta S surroundings. We just saw that delta S surroundings is Q surroundings over T, which can be replaced by negative delta H system over T. We now have delta S total in terms of delta S and delta H, both of the system, and that's positive. Well, if we want to get rid of the fraction, the delta H over T, negative delta H over T, we can multiply both sides of the inequality by T. So T delta S system minus delta H system is greater than 0. We're just kind of cleaning up our relationship a bit. And then, since Gibbs free energy, delta G, is delta H minus T delta S, and this equation initially had T delta S minus delta H. In other words, it was reversed or negative of the expression for delta G. Then if a spontaneous process has T delta S minus delta H greater than 0, then it has delta H minus T delta S less than 0. And this is basically where Gibbs free energy comes from. It's taking the second law of thermodynamics, which looks at the entropy change of the system and the surroundings, so the total entropy change for a process for the whole world, and it then relates that to enthalpy and entropy changes just for the system, because those are things that are more what we're interested in a lot of times, and then that gives us our way of looking at spontaneity in terms of Gibbs free energy. So we can do either one. We can look at Gibbs free energy change, delta G of the system is less than 0 means spontaneous, or we can look at delta S total, and delta S total greater than 0 means spontaneous. And for a specific example, here's the reaction of propane gas with oxygen, so combustion of propane. Delta H and delta S are given. And if we calculate delta S surroundings, it's negative delta H system over T, as we saw, and that's negative 2,219 kilojoules divided by 298.2 Kelvin if we're at 25 degrees Celsius. And that works out to be a positive number, pretty big positive number, 7.44 kilojoules per Kelvin, or 7,441 joules per Kelvin. Now, that creates a lot of disorder, or that's a lot of disorder in the surroundings due to this combustion reaction. Delta S total is delta S system plus delta S surroundings. Delta S surroundings is negative 375 joules per Kelvin. Delta S system is negative 375 joules per Kelvin. Delta S surroundings is 7,441 joules per Kelvin. That really wipes out, overwhelms the negative delta S value for the system. And so delta S total is a very big positive number, 7,066 joules per Kelvin, which means this process is very spontaneous. Here's a way to look at this kind of visually. There's a propane molecule, and there's some oxygen molecules, and then the molecules out here, the surroundings molecules, are just represented by these sort of purplish spheres. And if this reaction takes place, you create some carbon dioxide and some liquid water if you let everything cool back to 25 degrees Celsius, and that doesn't increase the entropy of the system. The system's entropy actually goes down. But remember, the combustion gives off a lot of heat, so although delta S system is negative and the entropy of the system goes down, we also have heat given off, which increases the entropy of the surroundings. So the entropy of the surroundings goes up quite a bit due to the heat from the reaction, and enough to make the entropy change of the universe a positive value, or the entropy of the universe increase. And then, of course, we could do this just in terms of the reaction. Delta H and delta S allow us to calculate or determine delta G. Normal things we've done before, plug in values for delta H and delta S. Don't forget to pay attention to units and get everything to work out properly. And that gives us negative 2,107 kilojoules, a very big negative number. So that also tells us this process is spontaneous. And that's it for screencast number 2.